Alright, welcome to today's contemporary math lesson. This is 13.2, Misuses of Statistics. So when we think about statistics, are statistics good or are they bad? And statistics can be extremely beneficial tool when used properly. Sometimes, however, statistics can be used to mislead people. And people can oftentimes use statistics to say things to benefit themselves rather than just tell the truth. So as we're going to be looking at some statistical statements today, we have four main categories of questions we want to ask ourselves to examine the validity of those statistical statements. So number one was the sample unbiased and of sufficient size? So that's dealing with the sampling techniques that we dealt with last class period. Number two, is the statement ambiguous in any way? Can you interpret it in more than one way? And a couple things to look out for here. One is the average. So when people use the word average, there are actually four different averages that we're going to be looking at, and you can find them in different ways. And so one set of data could have four different averages, so don't really know what average means. Other words are words like largest or smallest or fastest, all this other type of quantifiers here, and it needs to have an accompanying word. So for largest, how is it the largest? Okay, is it the largest in area, largest in sales? It needs a little bit more description there. A third question is, does the statistical statement lead to an irrelevant conclusion? In other words, so do the statistics that they're putting forth really lead to a specific conclusion? Are they related, or do they just sound good, and so you might think that it leads to a conclusion when it really doesn't? And a fourth one, was any other important statistical information omitted? Okay, so sometimes this is hard to tell, especially if they omit it, right? We don't know if there were other statistics. But maybe there were some other things that could have contributed to the findings. So those are just four of the things that we have to look out for. So let's take a look at some examples. Example A here. It says 4 out of 5 dentists recommend sugarless gum for their patients who chew gum. So there's a couple things we want to look here. Whenever it says 4 out of 5 dentists, all right, that number has been reduced, and there's really no way to know what the sample size is. So here, the sample size is unknown. All right, and there's one other thing we want to look out for here. It says for their patients who chew gum. So we don't really know if 4 out of 5 dentists recommend that you chew sugarless gum. But if you have to chew, well, then it's obviously better. But perhaps dentists may not even recommend chewing gum at all. All right, let's move on to example B. In a golf ball commercial, a type A ball is hit and a second type B ball is hit in the same manner. The type A ball travels further. Therefore, type A is the better of the two balls. So in looking at this, a couple things we want to look at. It says type B ball is hit in the same manner. So it really doesn't say that it was hit exactly or there was a machine hitting the ball. If there were just a regular golfer hitting the ball, it's very possible that the two hits could be different. Which leads us again to the sample size. Okay, was this experiment only performed one time? It just says in a golf ball commercial. So we're looking at this one experiment and this one time it happened. Is that really enough sampling to say that one ball is better than the other? Also, if these two trials were taking place at different times, who's to say that the conditions are exactly the same? So the wind could have shifted. Lots of different things could happen here. So we kind of have some omission of data and kind of an irrelevant conclusion based on this one single trial. All right, moving on. Example C. During contract negotiations, an employer states that the average salary of its employees is $35,000, whereas the employees' union states that the average is $30,000. Who should we believe? Okay, so obviously the employer is going to say that their employees make more money, and the union is going to say that they make less money because they want to make more. So again, when we're looking at this, the word we want to watch out for is average. So because there are 4 different averages, we really can't tell which one they used. Okay, so really, they both could be telling the truth. Since it wasn't stated how they found their averages, though, we really don't know whose side we can take. So certain averages will tend towards a higher number, and certain may tend towards the lower. All right, moving on to D. It says Joe's Toyota claims that it is the largest car dealership in the valley. So buy your car at Joe's. So right here we have another ambiguous word, largest. Okay, largest what? Largest in lot size, largest in selection, largest in sales. Really need to have that, that specificity. All right, let's keep on going. Letter E. A disinfectant manufacturer claims that its product killed 40,760 germs in a laboratory test in 5 seconds. Therefore, to prevent colds, you should use our disinfectant. So when we look at this, the statistics are saying that germs were killed. And their conclusion is based on preventing colds. So what I see here is a disconnect between the statistic and the conclusion. So I would say that this is an irrelevant conclusion. Okay. The relationship between germs and colds just really isn't valid. All right, moving on. Letter F. Company C claims that its paper towels are heavier than its competition's towels, therefore they hold more water. So if we look at the word heavier, okay, they're trying to say that more weight equates to holding more water. But is that really true? So I would say this again is an irrelevant conclusion. Okay, so the question is, does more weight equal more absorption? If you use that logic, you take a rock. A rock weighs more than, a paper towel, but doesn't necessarily hold more water. All right, letter G. An insurance advertisement claims that in Duluth, Minnesota, 212 people switched to insurance company Z. Therefore, since it is getting more customers, you should switch too. Kind of jump on the bandwagon. So what I'm looking at here, it says 212 people switched. Okay, I'm wondering if some stats were omitted. Okay, so it says 212 people switched to the company, but it doesn't really say why. That could be some important information. And it doesn't say how many people might have switched away from their company to another one. Alright, so that one's kind of lacking a little bit of information there. Moving on to letter H. It says a foreign car manufacturer claims that 9 out of every 10 of a popular model car it sold in the U.S. during the previous 10 years were still on the road. Okay. By the way, the manufacturer has only been around for a year, and this was not mentioned in the ad. So this is obviously an omission, but their claim leads people to believe that the cars are long-lasting. Okay. However, since they've only been around for a year, they could have said, hey, in the previous 100 years, that all the cars that we've sold are still on the road. But it would still really only be 1-year-old cars. So this is definitely an omission of some statistics. All right, next we're going to take a look at misleading charts and graphs. This is one area that marketing advertisers really use because visually we can be stimulated by these graphs without actually looking at the numbers. Okay, because the numbers and statistics are really the only thing that matter, but visually we can tell a different story than what the numbers are telling. So when looking at graphs and charts in two variables, you need to take the use of different scales into consideration. So the graphs can look visually very different while showing the exact same information. So they can either be used to maximize by zooming out of the data or exaggerate by zooming closer to the data. So let's take a look at this certain stock price right here, and it's rising over a certain amount of months. So if we look at this one right here, this scale starts at 0. So I would say that this data is really zoomed out. And when you do this, it's going to minimize the difference. So it's really zoomed out, starting at 0. In this scale right here, this actually shows the exact same data as this one. So you can see here right at 25. All right, January is at 25. And then it ends here about 33 or so. And right here it ends at 33. So it's showing the exact same data, but visually this looks like it's increasing much more rapidly. Here's the reason. When you break that vertical scale and you start it at a higher number, you really zoom in on the data and it's going to make an exaggerated difference. So this is zoomed in and it exaggerates the difference. All right, and part B over here is just another example of the exact same thing. So the one on the left, wow, 2002, that was really low. 2003, wow, that's super high. Okay, but if we take a closer look and we zoom out on the data starting at 0, you can see that 2002 and 2003 actually are fairly close. So again, it all depends whether you break the scale using this little notation here, or if you start at 0. All right, moving on. Here we have a circle graph, and this is the top 6 reasons Americans say they use the internet. So we kind of surveyed some people, and we put this into percentages. So in circle graphs, we are always using the percentage of people here. Now, if you look at the entire graph, this should add to 100. Okay, so that it shows the whole circle, 100%. But let's take a look and see what we actually have here. So 42, 37, 24, 16, 15, and 49. This gives us a total of 183%. So there's no way that in one circle we can have 183%, and it doesn't even make sense if we were splitting it up. So something is definitely going wrong here with this circle graph. Another way researchers can mislead people visually is they can take a statistic as simple as this. So something was $1 this year and it costs $2 next year. Okay, the true ratio here is really $1 to $2. Okay, so like one item to 2 items. Okay, and this would be a visually correct way of displaying that. However, as soon as you turn this into an area, so this would be a square with the side of 1, all right, this would be a square with the side of 2. So we still have this 1 to 2 relationship in the lengths of the square. However, when we look at the area, okay, the area of this one is 1, and the area of this one is actually 4. So the area has a ratio of 1 to 4, and visually, that's what your eye is going to pick up on. So next year looks actually 4 times bigger than this year. It gets even worse if we look at 3-dimensional shapes. So here, if this is a cube made up of sides of 1, here this cube is made up of sides of 2. So there's your ratio 1 to 2. However, if we're looking at volume now, the volume of this year is 1 times 1 times 1, which is 1. The volume of next year is 2 times 2 times 2, which is 8. So effectively, we've taken the ratio of 1 to 2 and made it visually look like 1 to 8. So this volume is 8 times bigger. Kind of messes with your head a little bit. So let's give this a try. And we want to master the art of deception here a little bit. Now, it's not always bad to do this because sometimes you want to show the differences and highlight those, and that's not a bad thing. So here it says, draw a line graph that makes it appear that the student on the last 5 quizzes has been improving drastically. Okay, so if we want a drastic improvement, what we have to do here is break the scale. So we're just going to break it like that. And we're going to really zoom in on this data here. So it starts at 62, 64, 67, 69, 70, up to 70. So just to make things nice, we can start here at 60. And then we could maybe go up by 2s. So 62, 64, 66, 68, and 70. So you'll see here we kind of spread out the range over the entire vertical axis here. Now on the horizontal, we usually don't mess with that too much because it's just a quiz score. So spreading them out wouldn't really help. But we just have quiz 1, 2, 3, 4, and 5. And then we're just going to go ahead and make a scatter plot here. So for quiz 1, we were at 62%, which is right here. Quiz 2, 64%, which is right here. Quiz 3, 67%, which is right about here. Quiz 4, 69%. And then quiz 5, all the way up here at 70%. So you can see this trend looks like these scores are increasing pretty dramatically. So you might want to, draw this graph if you're trying to convince your parents that you've been really working hard and they should let you go out this weekend. Alright, so let's try this now. And let's make a graph that shows that the student's been improving, but really not very much, very slow improvement. So what we're going to do, if we want to make something look minimal or increasing slowly, we're going to actually start our scale all the way down at 0. Alright, and we're just going to go up here maybe by tens. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So it makes sense going up to 100 because, quiz scores can go from 0 to 100. Now, if we take a look at the scores, we got 1, 2, 3, 4, and 5. And let's plot these here. So quiz 1 was at 62%, so 50, 62 is right about here. Quiz 2 is at 64, so it's a little bit higher. It's definitely going up. Doesn't look like very much. Number 3 is going to go up to 67, so we're still in that 60s range. Number 4 is going up to 69, so that's a little bit higher. And then number 5 is going to be all the way up at 70, so that'll be right at the 70 mark. So here you can see that the scores are improving, but it's going up very slowly, and you can see that there's still a lot of room for improvement here. So maybe your parents would come back with this score and say, hey, you gotta put in a little more work before we're going to let you go out. Alright, so that's misleading statistics.